All right, everyone. Welcome back. Just want to quickly, so my name is Sam Blau. I'm a postdoc in Christine Pearson's group. And I'm going to be teaching you a range of more advanced MongoDB functionality. But first, I just want to make sure that everyone can find the files for this lesson. So this is in 04 underscore Mongo underscore part 2. And I'm going to be walking through a partially unfilled exercise, or excuse me, lesson notebook. You have an already filled lesson notebook that you can follow along in. And then you also have exercises, the exercises notebook, which has all of the unfilled exercises for you to do in the 10-minute chunks I'm going to give you. But you also have the exercises solved notebook with the solutions for you to refer to. So starting here with this first lesson, I'm going to be teaching you about using distinct values, LM match, and regex. And we're going to start by instantiating our client and DB just as before. And I want to first look at one particularly exceptional laureate. And I'm going to do that by using the find one method. And this came up in the chat, actually. So here I'm going to look for a laureate that has won 3 prizes, which means that the prizes.to, the third element, 0, 1, 2 of the prizes list should exist. So exists true. And what we're going to find is actually, this is the Red Cross. International Committee of the Red Cross has won 3 peace prizes. And an interesting thing to note is that their gender is listed as org, an organization. That makes sense. And so here what we want to do is maybe you think, okay, well, if gender can be org, maybe let's be sure what the distinct values are that gender could take. And so we're going to say db.laureates.distinct, and then we're going to pass the field that we want to know the distinct values of, gender. We're going to hit Shift Enter, and we're going to get a list back. And we're going to see that there's going to be male, female, and org for organization. So this is a convenience method for common aggregation, distinct, kind of like count documents, but with different functionality, of course. Now, we're not going to cover custom aggregations in this lesson, but the aggregate method is powerful, and I encourage you to dig into it a bit on your own. But distinct aggregation is efficient if there's a collection index on the field that we are getting the distinct values of. Here, the field was gender. We're going to learn a bit more about how to create index later in this lesson, but for now, we don't need an index because the collection fits in memory and has less than 1,000 documents. So let's keep using distinct, showing some more examples of how you might use this. For instance, let's look at the distinct categories. Distinct prizes.category. So here we see that the 6 different Nobel Prize categories are physics, chemistry, peace, medicine, literature, and economics. And maybe what if we wanted to know the prizes, the categories, excuse me, where there had been laureates who had won multiple prizes. So we would say distinct. We're looking for the distinct values of prizes.category, but now we're going to filter for when prizes.one exists is true. And this tells us that the only categories in which laureates have won multiple prizes are chemistry, physics, and peace. And as we'll see later, that can be chemistry and physics, or chemistry and peace, or 2 physics. So now what I'm going to do is every time at the end of kind of a topic, I'm going to provide an example, slightly more complex. And for instance, in this example, I want to know in which country have USA-born laureates had affiliations for their prizes. So we're going to do db.laureates.distinct. So we want the distinct values of prizes dot affiliations dot country, and we're going to filter on, oh, hold on, filter on born country USA. And we see that all of the laureates born in the US, they have had prizes affiliated with the US, Denmark, Australia, and the United Kingdom. Okay, we're now going to move on to the LM match capability. So let's say we wanted to count the number of documents which for laureates which had won a prize in physics, category physics, and share one. That would be an unshared prize. So I've already filled this cell out. I'm going to go ahead and execute it. And we see the answer is 0, but we know that can't be true. We know there are certainly laureates who have won unshared prizes in physics. But the problem is that the way that we've set up this filter, we are forcing the prizes, the value associated with the key prizes to exactly equal this dictionary. Category physics, share one. But we know there's lots of other information there. We're not trying to limit it so much. We could instead count the documents where we explicitly say prizes dot category is physics and prizes dot share is one. And if I evaluate this cell, we're going to find 48 documents that match this criteria. But LM match allows us to be even more specific. And what we'll see, so here now instead, we're going to pass prizes, opening a dictionary with the LM match operator, and itself, that value is going to be a dictionary with category physics and share is 1. And if we evaluate this cell, we're going to see that this is 47, a different number than 48. Now, why are these numbers different? Well, let's take a look at one specific laureate, db.laureates.find one, first name Marie. And this is going to show us the entry for Marie Curie. And what you'll see is that Marie Curie has won multiple prizes, one in physics, which she got a quarter share of, and one in chemistry, which she had the full share of. So looking back at this example, we see, Marie Curie was included in this first count documents cell evaluation because she has a prize dot category that is physics and a different prize that is share one. And LM match narrows the results to ensure that a single entry, a single prize is both the category physics and share of one. So subtle difference, but can be critical for accurately querying data with subfields which you want specific to have specific composition. Now here's another, we're going to finish off LM match with another example. Now this example, the question is, what is the approximate ratio of the number of laureates who have won an unshared, aka share equals 1 prize in physics after World War II, which means the year would be greater than or equal to 1945, the ratio of that number of laureates to the number of laureates who have won a shared prize in physics after World War II. And the way we're going to evaluate this is by defining two filters. First, we've already predefined the unshared filter, where we use the LM match prizes. LM match category is physics, share is 1. This is an unshared prize, year greater than or equal to 1945, after World War II. So that would filter for laureates with unshared prizes. How about for shared prizes? So I'm just going to copy this down here. And now we know that share, instead of being 1, has to be greater than 1. And if we evaluate this, we see that about 12% of laureates, of physics laureates, after World War II were unshared. The vast majority of physics prizes after World War II were shared. Now moving on, the final topic of this lesson is using regular expressions. These are super powerful. I use them every day in my research. And here's an example where I've already constructed a distinct call where we're looking for the distinct values of born country, filtering where born country matches the substring Poland. So the regex operator by default is going to match any string containing Poland. So this can be Russian Empire, now Poland, just Poland itself, Free City of Danzig, now Poland, Poland, now Ukraine. Any of these strings contain the substring Poland and thus will be found by this filter. However, we can be, regex has a lot of powerful options. I'm just going to show you a couple of them right now. For instance, we could just look for substrings which have Poland at the beginning of the string. We would use the caret character, and then I would say Poland. And now we're only going to find the substrings that start with Poland. We could also further narrow down to things that were Poland but are now something else. So we're going to start caret Poland, but now we also want to do open paren now. And you'll notice that I did a backslash before the parentheses here, which is something when you're defining special characters within a regex string, you will usually need to do a backslash. So now when I execute this cell, I see Poland, now Ukraine, Poland, now Lithuania, etc. You could also match the end of a string. So for instance, we could say now Poland, close paren with a backslash before it, $sign. So it's the $sign that indicates this is going to be the end of a string. And so now we see the 6 entries that are now Poland but weren't originally. And just to end this lesson with another example, so there are 2 laureates with Berkeley, California as a prize affiliation city that have the initials GS, Glenn Seaborg and George Smoot. So this example, the question is how many laureates in total have a first name beginning with G and a surname, aka last name, beginning with S. And so here we're going to construct db.laureates.count documents where we want, remember, a first name starting with G. So we're going to do regex colon outside the regex. And we're going to do the caret starting with G. And then we want a surname, which is the key for last name. And that's also going to be regex and starting with S. And we get a type error because I have done something wrong with my collection. First name, count documents, db.laureates.count documents. Count documents. There we go. A typo in the function call. So there are 10 total laureates who have a first name G and a last name S. And we're going to return to the GS crew, as we call them, in some of your exercises. So for the next about 7 minutes, go ahead and start working on some of these exercises. Now, I'm not going to explicitly go over the answers here. I've given you quite a few exercises. I don't expect you to necessarily have time to do all of the lesson 1 exercises right now, but I think it's really important to actually take the time to kind of wrestle with some of these. You have the answers in the exercises solutions notebook, and I'm happy to answer any of your questions in the workshop 2020 chat. So go ahead and dig into some of these exercises, and we'll come back together in 7 minutes for the next lesson. Okay, everyone, I hope you found some of those exercises instructive. Especially after a full day of learning, being taught a lot of different concepts in Python, it's important to really solidify your understanding by taking the time to wrestle with some exercises. Okay, so here we are moving on to the next lesson, where we're going to be talking about projection and sorting. Now, what is projection? Well, it's reducing data to fewer dimensions and asking certain data to speak up so that you can find it more easily. Or kind of a classic projection that we're used to seeing is the projection of the world map, such as the Mercator projection versus the Gallup-Peters projection. Now, for our projections, we're going to be using the db.laureates.find method, and we're going to pass first the filter, which we're going to pass as an empty dictionary. And then we're going to pass the second argument is the projection. And if we execute this cell, we return a cursor, which we need to make into a list for in order for us to look at the contents. You could also iterate over it with an iterator, but we're going to do the simpler route of a list for now. And here we're just going to look at the first 3 elements of the list. So here, since we've passed an empty projection dictionary, by default, it only displays the ID field. But for instance, if we want to project out the prizes.affiliation field and maybe turn off the ID field, since it's pretty useless, we would instead do list. Actually, I'm just going to copy this whole thing down. List db.laureates.find, and now we're going to do prizes.affiliations. And in order to turn this on in our projection, we're going to make that value be 1. And then we're going to turn off the ID field of 0. And now if we execute this cell, we see the first 3 elements of this list, where now we're just seeing the prizes.affiliation being Munich University, Leiden University, Amsterdam University, etc. One useful thing that you might want to do with a projection is to not have to worry about if a certain field is missing in your document. So for instance, we could do db.laureates.find, and we're going to do gender org. So remember, we have those organizations, and that's our filter. We're looking for organizations, and now our projection, we're going to turn on first name 1, born 1, and we're going to turn off the ID field, ID 0. And now if we look at the resulting list, we're going to see the Institute of International Law, Committee of Red Cross, and for almost all of them, they have both a first name and a born date, the year in most cases that the organization was established. However, for the National Dialogue Quartet, we don't see a born date. And by using a projection like this, even when you have an entry that might be missing a given data field, it's not going to throw an error, and you're still going to be able to collect the information that you care about. Now here's an example to end our little projection section, where we're looking at the laureates of the 1963 prize in physics and how they split the prize. So here is a query without projection, where we're using LMMatch, specifically category physics, year 1963, and we're doing this on the laureates collection. So now, how would we fetch just the laureates' full names and prize share info? So we construct a projection, turning on first name and last name, aka surname. And then we also want the prize share info. So that would be prizes.share 1, and we don't want the ID field. So we're going to turn that off. And here I've already put the projection in the call. So I'm going to go ahead and execute the cell. And here we see that the 1963 prize in physics was 50% for Eugene Wigner, a quarter for Maria Gopert-Mayer, and a quarter for Hans G. Jensen. So moving on to sorting, sorting is super useful function in Python and code in general. Here, I first want to talk about sorting post query. So here we're using this operator library, and specifically the item getter functionality. So here I've already populated a cell where we do db.prices.find. We're looking for category physics and projecting out the year 1. And then we're going to sort the resulting docs used by the year. So if I execute this cell, we're just projecting out the years, remember? And so if we sort by the year, we're going to get in ascending order 1901 to 1905, where I've just grabbed the first 5 elements of the list here. Now, what if we wanted to do that in descending order? I'm just going to copy this entire block of code down, and so now in our sorted call, we're going to put reverse equals true. And now we're going to have the result in descending order from 2019 going down. But we can also do sorting in query in MongoDB. And so now we're calling the same prizes.find call, still filtering on physics, projecting out the year, but now we can pass a sort field, where the sort is going to be a list of tuples. And here, if we execute this cell, we're again going to see the years in ascending order, thanks to this one value in our tuple. We can just copy this down again and instead pass year, comma, -1. That essentially does exactly what reverse equals true did before. So now if I execute this cell, we're going to have 2019 counting down. But one thing that's really powerful is that you can actually have both multiple levels of sorting when you're doing, when you're doing a MongoDB sort call. So in this example, we see this is a list of tuples. Again, before our list had one tuple, now our list has two tuples. And we define this as a primary sort is the first tuple, and a secondary sort is the second tuple. So here we are sorting ascending by year and descending by category. And here we've done a slightly more complex filter, year greater than 1966, less than 1970. And we're projecting out category and year and turning off the ID. So now I'm just going to execute this query, and we see that we first and foremost have primary sorted ascending by year, 67, 68, 69. And then we have reverse alphabetical sorted the categories. Physics piece, right? So it's CLMP reverse. And you'll note that economics shows up here. This is 1969 was the first year that the prize in economics was awarded. So just to finish off this section with an example, the block here prints out the first 5 projections of a sorted query. And here we're looking for laureates who are born greater than or equal in the year 1900 or later, but won prizes in the year 1954 or later. And we're only going to look for men and women right now, no organizations. And that's the filter. Then the projection, we're projecting out the year they were born, and the year of the prize, and turning off the ID field. And the question is, by looking at the result of this call, what needs to go in this sort field? And so looking at this data, we see, if we just first look at the born years, we don't see an obvious sorting order. But if we look at the prizes year, we see that first and foremost, it's sorting ascending by year. First 3 all won prizes in 1954, the next 2 in 1955. Then within the year, we can see that all 3 laureates who won prizes in 1954 are now reverse sorted by their birthday. So what we can do, I'm just going to copy down this code block, and I'm going to define my sort. I'm going to insert that here. And so this is a list of tuples. So I'm going to make a list. The primary sort is prizes.year in ascending order. Not a colon, a comma, because it's a tuple. And then a secondary sort by born. And as we can see, this is descending. So we're going to do -1. And if we execute this cell now, we recover the data shown above. So that finishes off the projection and sorting lesson. I encourage you to move on over to the exercises. And as we go, there are now fewer exercises associated with projection and sorting, but they're slightly more complicated. So take a look. They incorporate things like regular expressions that we learned last lesson. So we've got about 10 minutes to dig into those exercises, and feel free to ask any questions in the Workshop 2020 Slack channel, and I will answer them. All right, I hope you found those exercises instructive, and just a reminder that you do have these solutions in the exercises_solved notebook. So feel free to consult them, but definitely do take the time, if you have it later, to finish working through the exercises and solidify your understanding from today's primer. All right, the final lesson of this block is about indexing. So what are indexes? Well, you can think about it just like an index for a textbook. For instance, maybe you open up materials science for engineers and you want to know what page eutectic temperature is mentioned on. So you go to the back, you look in the index, you find where it's the page number that's listed, and you can go right to that page to find the answer that you're looking for. So, kind of the question to know is when to use indexes. When are they important? Is for queries with high specificity, when you're querying large documents or querying large collections. So first things first, let's make sure we understand what indexes are currently present. So we're going to look at db.prizes.index information. And we're going to see that I forgot to remove an index from the last time I was testing this. I'm going to insert a cell below. I'm going to do db.prizes.drop index year -1. Lovely. Yes, a tuple. Sorry about this. If you are not careful and you don't drop your index, it will stay present on your local DB. I'm just going to drop that index. So now if we look at our index information, we see that we only have an index on the ID, and that's by default. You're only going to have an index on ID. So now let's gauge our performance before adding indexes. So we're going to be using this %% time it, which is a super nice Jupyter Notebook functionality to get some timing. So we're going to do a list of db.prizes.find, where we're passing year 1901. And I've made a mistake again. db.prizes.find. There we go. So now this is running a time it. So it's going to run this call a bunch of different times and give us some timing information. Specifically, this takes on average about 650 microseconds. What if we did a different time it call? Time it docs equals list db.prizes.find. Now I'm going to pass an empty filter, but I'm going to pass a sort on, which is a list of tuples year 1. So this is find my documents sorted by ascending year. And now this takes substantially longer, about 7.5 microseconds or milliseconds, excuse me, on average. And we could also do the same thing, but with a different sort. I'm just going to copy this down to -1. So now we're doing a reverse sort, a descending sort, and we're going to see that that takes even a little bit longer, 7.72 milliseconds on average. So what we could do if we wanted to speed up some of these calls is to add a single field index, where an index model is a list of field comma direction pairs. So we would do db.prizes.create index, and here we're passing a list of tuples year comma 1, and that is going to say, yes, I've made you an ascending year index. So now if we do our db.prizes.index information, now we're going to see both the baseline ID index and the year_1 index. So now we can just grab some of our examples above and execute them again and see if we've sped things up. So originally this was 650 microseconds, now it's down to 432. We're going to see that the sort is also going to come down substantially from about 7.5 to just over 6. And the reverse sort is also going to come down a bit. Was previously 7.72, and now it's 6.46. Now, it's always, as you saw before at the beginning of this lesson, I had an extra index on my local machine because I had forgotten to drop an index after I created it. So just for consistency, it's always a good idea to drop your indexes. I mean, in reality, if you find an index that's worth creating, you're going to create it once and be happy that it stays. But for testing, it's always important to drop an index when you're done using it. And when you execute that cell, it's not going to print anything out. But now if we do our index information again, we're going to see that index is gone. Now, just as an example here, or we see thus far, I've just shown creating indexes with a tuple that has a +1 in the value, but you could also do a -1. This would be a descending year index. And just as an example, now this doesn't always work exactly as I'd hope, but in principle, if you have a descending year index, then a reverse sort should be faster. And that's exactly what happens here, is that when we had an ascending year index, yeah, it sped up our reverse sort from 7.72 milliseconds to 6.46. But if we instead had a reversed year index, it sped it up even more. And that makes sense. If you're sorting in the exact same direction as your index, you would expect for the sort to be sped up more. So now I'm just going to go ahead and drop that index for consistency. Okay. Now, another thing that we can do is to add a compound or multiple field index. For instance, let's say we wanted to time it. We're going to do a list of db.prizes.find. So here we're going to do a filter. Category is economics. And then we're going to project out year, going to turn on the year and turn off ID. And we're going to see how long that's going to take. So now we're passing both a filter and a projection. And we're going to see this is about 785 microseconds. So now we can create db.prizes.create index. And now we're going to do a list of tuples. We're going to index a compound index, both on category, ascending, and on year, ascending. We're going to go ahead and create that index. We're going to copy down our example and see how much we've sped things up, down to 525 microseconds. So a bigger improvement, since now we're executing a more complex operation. The compound index gives us even more bang for our buck, if you will. And we're going to go ahead and drop that index for consistency. Drop index. So now an even more complex operation. Here we're doing a find one operation, filtering category economics, projecting out year, turning off ID, and sorting on the year. And so now we're going to create the exact same index we created above. And we're going to execute this find one. Oh, first I skipped a step. I'm going to get rid of that. Before we create the index, we're going to execute this time it and see how long now, since we're doing a filter, projection, and a sort, this should take even longer. And in fact, it does, 837 microseconds. So now we're going to create the index and execute the find one call again. And now we nearly halved our execution time. So the more complex your call, the more effective, the more of a speed up you're going to see from your index. And then once again, for consistency, we're going to go ahead and drop this index. So with that, you have just over 10 minutes to work on some indexing exercises, where we're going to start by figuring out designing the optimal index to get this execution time below 400 microseconds. And then we have a couple of exercises that kind of use indexes as well as the sorting and projecting functionality that we've seen thus far. So go ahead and take 10 minutes to work on these exercises. Please ask any questions either on CoCalc or in the Workshop 2020 Slack, and we'll come back together in 10 minutes to wrap up for the day.